Hello, everyone, and thank you for this opportunity. I'm Dan, and I'm a postdoc at Cornell University at the Department of Mechanical and Aerospace Engineering. Today, I will talk about part of my research that aims to better understand the impact that stratospheric aerosol injections would have on the stratosphere. The context for my research is global warming. We know that long term, only reducing our CO2 emissions and bringing them to zero will allow us to stabilize temperatures and avoid catastrophic damages. The problem now is that we need to do it fast enough to avoid reaching the temperature thresholds that were determined, for instance, in the Paris Agreement, well below 2 degrees Celsius above pre-industrial levels, but possibly below 1.5. Now, you can see in this figure the net CO2 emissions in the SSP scenarios aimed at informing the latest IPCC report. And to have a chance to stay below 2 degrees throughout the entire century, the cut in emission has to be pretty steep. So the real problem is what happens if we cannot do this cutting fast enough and we end up going above some of these thresholds? Is there something temporary that we can do that can avoid some of the risk attached to going over those thresholds? Here is where the concept of SRM, or solar radiation modification or climate engineering, comes in. SRM is the deliberate modification of the Earth's climate through the reflection of a portion of the incoming solar radiation in order to reduce some of the risks produced by global warming. And the figure you see here on the left comes from a report from this year from the National Academy of Science, Engineering and Medicine, where the need for further research on this topic and on the possible impacts and feasibility of climate engineering was discussed. In particular, I focused my research on the first of the three methods, stratospheric aerosol injection. SRM done through the injection of sulfate aerosol precursors in the stratosphere in order to mimic the effect of explosive volcanic eruptions. We've observed during the 20th century that explosive volcanic eruptions tend to cool the planet for a couple of years after they happen. And the idea that was originally proposed by Paul Crutzen in 2006 was to mimic this effect artificially in order to reduce surface temperatures. When SO2 reaches the stratosphere, it undergoes a rapid process of oxidation through OH. Even under the case of a volcanic eruption, when large quantities, up to 10 or 20 teragrams of SO2 are injected in the stratosphere, the whole cloud can oxidize in a couple of weeks up to a month. This process of oxidation ultimately produces H2SO4 in vapor form, then combine with the water vapor already present in the stratosphere and produce aerosols. These liquid aerosols are usually of a size that varies between 0.3 and 0.5 micron in diameters, and that's what we observed after volcanic eruptions. The growth of particles can be determined not only by the formation of new particles, but also from the condensation of H2SO4 vapors on existing aerosols, or on the conjunction of more than one particles, keeping mass the same but reducing the number concentration of these particles. The size of the particle is very important because at those sizes, they're exactly in the optical window where they can maximally reflect the incoming solar radiation. That's not the only thing that these particles do, however. They would also absorb part of the outgoing planetary radiation and part of the incoming solar radiation, and so locally warm the stratosphere. And this effect, as we will see, is particularly important in determining changes in dynamics and chemistry in the stratosphere. Once the aerosols are formed, there are various factors that control where the aerosols go and their distribution in the stratosphere. Here you can see a figure from some simulations where we injected 5 teragrams of SO2 at the equator between 18 and 25 kilometers. The distribution is not uniform, neither in altitude nor in latitude, and There are three factors mainly that drive how the distribution looks like. The aerosols produce an heating, as I said, and this heating results in a self-lofting of the aerosols, so they tend to push themselves up a little bit. They also follow the large-scale stratospheric circulation, so the Bird-Dobson circulation. So even if we inject the equator, they will be moved out of the tropical pipe eventually and be distributed at all latitudes. The Bird-Dobson circulation will also remove them, and together with the Bird-Dobson circulation, also simple gravitational settling from the weight of these particles will ultimately move them out of the stratosphere into the troposphere, where they can be removed much more efficiently to the surface. The ultimate idea behind SAI is to affect surface climate. However, the effect that the aerosols have in the stratosphere and their perturbation also strongly affect the impacts that the aerosols would have at the surface. In this figure, I tried to convey how many things there are and how complicated these effects all are, and how different the actual injection of SAI would look in the models and in the real world compared to the idea of just turning down the solar constant in the models. In particular here, however, I just want to focus on the effect that these stratospheric aerosols would have on ozone. This is of particular importance because the WMO report in 2022 will have for the first time a chapter about how SAI modifies stratospheric ozone that I'm helping to write. So I want to present here a bit some of the research that I've done to support the new WMO report and to better understand what do we need to improve to get a better sense of what SAI would do to stratospheric ozone. In the climate model intercomparison project version 6 that was used in the latest IPCC report, there is a set of simulations that include geoengineering. They make use of two available scenarios, part of scenario MIP, SSP 585, where there is a high forcing due to a very high continued emissions of CO2, and a medium scenario with a lower net forcing that still produces a warming, but not as much as SSP 585. The idea behind the geoengineering simulations in CHEMIP 6 is to use either a reduction of the solar constant or stratospheric aerosol injection to reduce the forcing in SSP 585 so that geoengineering simulations follow the same temperature as SSP 245. Up to now, 6 models performed the simulations required for GeoMIP. After focusing on one of these models, CSM2 WACM, what you can see here is the green line represents the global mean temperatures under SSP 585. Over the century, CSM2 produces a warming of over 5 degrees from 2020 all the way to 2100. The warming under SSP 245, it's much lower, but still around 2 degrees. Now, what you see in the blue and red line are the simulations in which, with the same emissions as SSP 585, geoengineering is performed. So the global mean temperature in this model and in all other models manages to be as low as SSP 245, even under greenhouse gases concentration. Now, the models tend to agree that geoengineering can be used to reduce surface temperatures. However, there are a lot of things they do not agree on. Here I'm showing, for instance, the zonal mean stratospheric AOD in the last decade, and you can see how big the difference is between the models. There are models that show a lot of aerosols confined in the tropics and models that show the exact opposite. And models also do not agree on the amount of SO2 that needs to be injected to achieve those optical depths. This is important for what we're trying to understand because some changes to ozone concentration are driven by heterogeneous chemistry. So here I'm showing the surface area density in 3 models with comprehensive stratospheric chemistry that can thus simulate some of these changes. And you can see the big difference, for instance, between CSM2 WACM that has a large concentration of aerosols also in the tropics, and UKSM that has most of their aerosols in the tropics. Why is that important? There are two main processes that are driven by surface area density changes. One of them is the increase in N2O5 hydrolysis at the interface of the liquid acidic sulfate particles, and this would result in the production of HNO3, which is a much less reactive nitrogen reservoir. And this would then decrease nitrogen oxide and reduce the catalytic ozone loss cycle from nitrogen oxide. This reaction is most important in the mid and upper stratosphere above 30 hectopascal. And this effect would also be more important in the tropic and mid latitude. On the other hand, enhanced surface area density would result in the activation of halogens from reservoir species to species such as HOCl and the likes. And this would result in more ozone destruction. However, these reactions are most important below 200 Kelvin, and so in the polar regions. Therefore, where the aerosols go, it's very important to determine which of these processes dominate. This is not the only way in which ozone can change. Another possible change is through dynamical changes. As I said before, the aerosols warm the stratosphere. However, as you can see here, models do not agree on how much warming there is in the tropical stratosphere when aerosols are injected. Given a global stratospheric AOD of 2, some models simulate a warming of 2 Kelvin, some models simulate a warming of 10 Kelvin. So that's a huge difference. And this is important because there are various changes that are mediated by the changes in temperature. As I said, there is a self-lofting effect, so there is an increase in residual tropical vertical velocities. The QBO can change, the tropopause can warm, there can be a strengthening of the stratospheric polar vortex because of changes in horizontal temperature gradients in the stratosphere and an acceleration of the Beer-Dobson circulation. These can all lead to changes in ozone. If we warm the tropopause, there is an increase in stratospheric water vapor that increases some ozone loss. If we strengthen horizontal transport in the lower stratosphere, there will be more ozone at mid and high latitudes. If we warm the stratosphere, there will be changes in reaction rate significant for ozone production, and also a stronger polar vortex may result in more halogen activation and springtime polar ozone depletion. So in these three models under analysis, you can see that the changes in temperatures do result in somewhat robust changes in dynamics, but their magnitude is different. The strengthening of the polar vortex is there, and so is the change in vertical velocity in the tropics. However, there are some very big differences between the models. Overall, this means that models will simulate different amount of ozone changes depending on what's happening to the dynamics and to the aerosols. For instance, here you can see what happens in the last 2 decades of the experiments between 2080 and 2100 in these three models. And for instance, just look at the difference between CSN2 WACOM that sees a large ozone depletion in the southern high latitudes, versus UKESM that sees an increase. So overall, the simulated changes in the total ozone column that are shown here shows a very large uncertainty, especially for instance in the tropics or at mid latitudes. There is no agreement between the models of what would happen to the overall ozone column. So concluding, there's two kinds of uncertainties when discussing SAI impacts. One of them I did not discuss here, and is related to the scenario that we pick. When do we inject, where do we inject, and what do we inject, and how much do we inject, all will change differently ozone in the stratosphere. On the other hand, there's an uncertainty that is related to the model that we use to simulate these changes. How are the aerosols distributed? What's the radiative response in the lower stratosphere? What's the radiative response at the surface? How did stratosphere respond? And what are the chemical processes that are included in the model? In this figure, I tried to give an idea of all the physical source of uncertainties for SAI when it comes to the impacts. And as you can see, all of them are connected with one another. And they all need to be solved in one way or another if we want to try to understand what the overall impact of SAI would be. Thank you and happy to take questions.